Here we see the FUVE Michelson interferometer high resolution on optical baseplate. The effect of interference together with a precision drive on the plate is used to determine the wavelength of a laser light. This laser is guided into a Michelson interferometer equipped with a fine adjustment drive. When the length of the interferometer arm is varied with a fine adjustment, the interference pattern changes. From the known displacement, the wavelength of the laser light can be determined. Here we can see the complete equipment that we need for the setup. We have the FUVE optical baseplate, vibration damped, that comes in a case. This is very handy if you want to store away your experiment in dust-proof way. You take the lid off, of course, now, because now we want to start setting up the experiment. The optical baseplate is vibration damped, and most of the components are placed on it via these magnetic holders. They can move across the plate, but they are very sturdy, very hard to take off. So once the optical setup is complete, it will be very stable. Nevertheless, we have all possibilities to change the setting around. So now first we start with the setup by putting this extra plate with the fine drive on it on the first plate. By doing this, we assure that the coordinate lines run as parallel or coincide as much as possible. The next step is to introduce the laser, that is the main component actually of this experiment. We put it in one of the holders intended herefore. Before switching the laser on by this safety switch equipped with a key, we make sure that the beam can't hit anybody unintentional. It's best to place the screen that we use later on anyways just here, so the beam strikes the beam and nobody else. It is important that the level where the laser beam travels is always parallel to the plate. We recommend for this experiment to travel at about 125 millimeters above the plate. I first set this up for the laser this way. The next thing we have to do is to introduce one of the mirrors. First we have to set the mirror into its adjustment support so that it can be very gently swiveled around. We need a small screwdriver to fix this. We place the mirror in one of the magnetic holders, and then we put the mirror such a way that the laser beam is deflected by 90 degrees. We also make sure that the mirror is hit quite central by the laser beam. To ensure that it runs along this coordinate, we can make use of the screen. The mirror number 2 is now placed such a way that the laser beam is deflected towards the extra plate with the micrometer drive, and again runs parallel to a coordinate. Here we ensure again that the laser beam is still at 125 millimeter height. We can do this easily by using the adjustment screws of the support. Now we place the third mirror into the hole made therefore in this fine adjustment drive. Again, we ensure that it's hit in the center, but also that the reflection from the third mirror hits the second mirror exactly where it originates from. When we did this, we introduce one important part here in the setup, that is the semi-transparent mirror. We put it in an optical base. Again, when we place it, we make sure that the beam strikes it quite central, and that the one part of the beam that is reflected travels 90 degrees with respect to original beam, and the other part just goes through it and hits mirror 3. The last mirror, mirror 4, is placed on the additional plate with fine drive, again, so that it's hit by the laser beam in central. The laser beam that hits it now is the beam partially reflected by the beam splitter. We already see that now on the screen here in the back, two spots are visible. One stemming from mirror M4 and one from this mirror M3. Next step is to bring those two spots in coincidence by adjusting either the adjustment screws on mirror 3 or on mirror 4. In this case, I take the one of mirror 3, bring the two spots in adjustment. They are perfectly overlapping now, those two spots, and you can also see the first indication of interference. You see a slight flickering of the spot. That means our adjustment is quite good. We still don't see the rings that are necessary for this experiment, but the laser beam has to be expanded using the lens of 20 millimeter, also placed in the beam before the beam hits the interferometer. It is placed here in the first part of the path, and make sure, of course, that the beam runs directly central through the lens. Since I see some stripes, I can meticulously adjust the mirrors M3 and M4 so that finally we have a part of the ring pattern visible. Now that we have a set of rings visible on our screen, the adjustment for this experiment is done, and we can move on towards actually performing the experiment. That means changing the distance of one of the mirrors to the beam splitter and observing the interference pattern at the same time. To do this, the position of the mirror is altered using a lever armed with a transmission ratio of 20:1 and the micrometer screw. 2 complete turns of the screw moves this side of the lever by 1 millimeter. That means the other side of the lever is moved at the same time by 50 micrometers. On changing the optical path length, one sees also changes in the center of the rings. Maxima change to minima and vice versa. According to theory, a change of path length of one wavelength will turn a maxima into a maxima again. That means that our distance between the mirror 3 and the beam splitter is changed by half a wavelength. To determine the wavelength of the laser light, the change of distance between mirror 3 and the beam splitter is measured by reading the initial and the final value on the micrometer screw. At the same time, the maxima to maxima or minima to minima that pass the center of the interference ring pattern are counted. In a sample measurement, the mirror was shifted by 43.1 micrometers. At the same time, 135 fringe changes were counted. This means that the calculation results in a wavelength of 639 nanometers. One last hint. You can make the path of the laser light visibly very impressively if you use some smoke or fog.